All right, so today we're going to continue looking at simple linear regressions. So I trust that you all have the script, just like this one, right? So a brief recap what we did in the previous class. Well, first of all, what we're predicting really is can we put a price on a car which is sold at the used car dealership lot. Okay, so and you told me that there are a lot of variables that affect the price of the car, but probably the most significant of them all is mileage, right? How extensively the car was used. And that's what we did, right? So we read the data from the file, Corolla CSV. Then we, apparently, here what we did is scatter plot, right? X was our mileage, Y was our price, and this is what we found, right? This is how the points are distributed. Not exactly a straight line, there is some kind of a curvature, right? But in general, I can see that mileage goes up, price goes down, as it should, okay? And then we calculated the coefficient of correlation, right? We said that coefficient of correlation is, oh my god, where is that? Okay, so I'm going to run quickly all these things. Yeah, coefficient of correlation is negative 0.596. And according to our informal classification of correlation strength, we said this is moderately correlated pair, right? Mileage and price are correlated moderately. That means that, yeah, it's a predictor, but it's not the greatest predictor, or so it seems, okay? And then this was the most important thing that we did last class. We ran the model, right? And again, we used the built-in function. LM stands for linear model, okay? Price is our target, mileage is the only predictor, okay? And the data that we used was entire data set, Corolla data, right? And then, let me run this line, and then we looked at the summary. And summary is probably the most important output from all these analysis entirely, okay? So, I'm looking to write down my model as the linear function, right? My predictor is mileage, my dependent variable is the price, and this column which says estimate, it contains two most important outputs, right? So here is one, that's my y-intercept, that's the free term, and here is another one, the slope for the mileage variable, which is negative, as it should be, right? Because we see that the dependency is kind of inverse, right? Mileage goes up, the price goes down, so therefore slope should be negative, okay? And then from this output, this is the equation that we wrote, right? The price of the car is, here is my slope, times the mileage, independent variable predictor, plus the free term, which is the slope, right? And then we said, okay, we can insert actually a line into the graph, which looks like that, which basically tells you this is the best fit, right? Out of all possible lines, with all possible slopes and all possible intercepts, that's the one that kind of is the best, represents the point in the most fair, best fashion, okay? So let's start today by looking at interpretation of the model coefficients, okay? So here, let me write that down actually in the one note. So minus 0.063 mileage plus 15,816. All right. So here is my model essentially. Price equals minus 0.0681. Is that what it is? Got it already. 6313 times mileage. 6313 times mileage. All right. And plus 15,816, if I remember correctly. Let's see. $15,816, right? Okay, so here's my model, right? How do I, now what I want to do is give a plain English interpretation to the slope, to this one, okay? And to the intercept, this one right here, okay? Let's start with the slope, because it's kind of the one that we're going to use the most. Okay, how do I interpret the number negative 0.06313? Well, suppose I'm looking at two cars. Okay, one has some number of miles, which I'm going to call X. Okay, whatever it is, X miles. All right. Now I'm going to take the car and drive it so that the new mileage is going to be the old mileage plus 1. In other words, I'm going to go from X to X plus 1 mile. Okay? From X to X plus 1. What will happen to the price? Tell me. That's exactly right. The price will go down, right? By how much? Well, here, right? So let me call it old price, okay? Old price when the mileage was X. So now my new price is going to be the slope minus 0.06313, right? Times, now the new mileage is X plus 1, right? Okay, and the same intercept, same free term, 15,816, okay? And now I can basically rearrange things a little bit, okay? So it's minus 0.06313 times X, and then I'm going to have the free term, 15,816, but also there is a term that comes from this plus 1, right? So that is slope times plus 1, that is minus 0.06313, right? So over here, this portion is nothing, none other than my old price, right? When the mileage was still X. So this is old price. So what do I see? When I put an extra 1 mile on the car, right? My new price goes down by that much, right? So I have to add the amount of slope. Slope was negative, so the new price is 0.06313 of what, by the way? How do we measure prices? What are the units? Dollars, right? Probably. Okay, so the car that has the same amount of miles plus 1, the price is lower by 0.06313 of a dollar. So essentially it's like 6.3 cents. Right? That's my interpretation, okay? So my plain English interpretation for the slope is for each extra mile that I put on the car, the price drops by 6.3 cents. So if you're going to university from home, for example, right, and it's a 10-mile drive, then each mile that you put on the car reduces the value, market value of the car by 6.3 cents. So you drive 10 miles, your car just lost about 63 cents in its value, okay, just because it's more used now than it was in the morning, okay? Make sense? All right, cool. Now, how do we interpret the intercept? So again, here's my model, right? Price equals negative 0.06313 times mileage plus 15,816. Well, this one is actually even simpler, right? What happens if I set mileage to 0? Well, it means that the price becomes equal. This term essentially cancels out completely, right? And the price is equal to 15,816. How do we call the car that has mileage equal to 0? Brand new, right? So therefore, I can interpret, this is my intercept, right? I can interpret the intercept as the value of the brand new car with no mileage, okay, is $15,816, which seems reasonable, right? There are a couple of things, okay? Number one, each time when we interpret the vertical intercept, you have to be very careful, okay? Number one, the reason why you have to be very careful. It is possible, not in this problem, but generally speaking, it is possible that the 0, x equal to 0, is not in your range of values. Here's what I mean, okay? Suppose, for example, let's say I'm trying to predict the university GPA based on SAT score. Can I do that, by the way? And why would I be interested in predicting university GPA based on SAT score? What do you think? Admission, exactly, right? So universities require SATs, right? Why do they do that? Well, they believe that higher SAT scores are linked with higher university GPAs, right? So therefore, let's say here is my Y, and this is university GPA. I'm going to call it UGPA, okay? And here is my SAT scores, right? Let's say that I have a bunch of students. What's the realistic minimum you think that can get acceptance? Minimum SAT score where you can still get accepted to the university. How much? Depends on the university. Well, let's say generic pumpkin university anywhere out there, okay? 500. Okay, so 500. Nobody below 500 gets accepted, right? What's the highest SAT can be? 16. So therefore, we're looking somewhere over here, right? 16. So let's say I get a whole bunch of students, right, that were accepted to the university, and this is what it generally looks like, okay? And I can see that, hey, I can fit a straight line, right, into this cloud of points. So it tells me that as SAT goes up, the university GPA also goes up, okay? And let's say that my model is to predict the university GPA. That's an ugly G, okay? So I have to take, let's say, for example, 1.5 plus 0.037 times the SAT score, something like this, okay? So how do I interpret that one? Probably I need to include another 0. Okay, 0.00375. Okay, how do I interpret that one? Well, I can interpret that with each, let's see, 100 extra points on the SAT score, right? You multiply 100 by the slope, you get 0.37, something like that, right? For each 100 extra SAT points, the university GPA is predicted to go up by 0.37 on average, right? That's similar interpretation to what we had before, right? How do I interpret this one, the vertical intercept? Well, if SAT is 0, then your predicted university GPA is 1.5. Does that look reasonable to you? If your SAT score is 0, then at the university you will earn expected 1.5 GPA. Does that make sense? No, it doesn't, right? First of all, 0 was not even part of our data set, right? We didn't have any data in this area. So when we're saying that, yeah, you can interpret it like that, that means that we can project this line. Strictly speaking, this is the data which I used, right? It's in this range from 500 to 1600, right? I didn't have any numbers below 500. So when I'm saying that this is interpretation, 0 SAT university GPA is 1.5, it's kind of, I'm assuming that this line will keep going like that, which I don't know if it's true or not. May or may not be, right? So no data, no conclusion, basically, okay? So oftentimes this is the case. The reason why we cannot really interpret nicely the vertical intercept is because simply this is outside of our data interval, okay? 500 to 1600 in this case. 0 lies outside. We don't know how this equation behaves in this area. We don't have data for that, okay? That's one. Another reason why this interpretation, let's come back to this one, right? Price of the brand new car with 0 miles is 15,816 is actually right here in the graph, okay? We realize that this point right here, when my straight line hits the vertical axis price, is 15,816. This is y-intercept, right? That would be my prediction for the price of the brand new car with 0 miles on it, right? Do you see a lot of cars with low mileage that are around this point? No, not really, right? They're all up here, right? Why? Because apparently, from what it looks like, the data does not behave in a linear fashion, right? What do we see? Brand new cars, or cars with low mileages, they have high prices, right? And then you start driving the car, you can see that the price drops pretty quickly, right? And then somewhere around here, somewhere around 50,000 miles, it kind of flattens out and starts going down in a linear fashion, more or less. Do you agree? So the process, how quickly the car loses the value, is not linear. Okay? Originally, car loses a lot, and then it kind of flattens out. Have you heard that this popular saying that the moment when you drive the car from the parking lot, it becomes used, right? And loses, like some people say 10% of its value, some people say $2,000 or whatever it is, right? And that's probably true, right? That's why we see this big drop originally, and then it kind of flattens out, right? So this is another reason why interpretation of vertical intercept, as you know, this is the price of the brand new vehicle, is oftentimes problematic, because it's really not, okay, because we don't see a lot of cars priced around this vertical intercept, right? They're all priced high, okay? So bottom line is slope we can easily interpret almost in all cases. Intercept, not so much. More frequently you will find that there is a problem with interpretation of the vertical intercept, okay? So a lot of times it's just plain non-interpretable, okay? All right. Let's see, what's the next thing that I wanted to talk about? Let's discuss model accuracy, right? Because accuracy, every time when you do predictive analytics, and this is a predictive analytics, would you agree? We're predicting price of the car based on the mileage, right? Before that, when we did classification tree, we predicted which customers will agree to a loan if bank contacts them out of the blue, right, without being asked, okay? So what we're doing for several weeks by now actually is predictive analytics, okay? So each time when you have a model, you will have errors in the model, right? In classification tree case, it was accuracy and related measure, misclassification rate, right? And then we also had sensitivity and specificity, right? All of these were performance measures, okay? Well, how do we measure performance of model like this? We don't classify anything in this case, right? Our target is numerical. It's the price, right? So how do we measure the performance of the model? Well, let me go back to the drawing board. Quite little. One of the fairly popular measures of how we evaluate the accuracy of regression model is something that's called coefficient of determination. Coefficient of determination. Or also known as what? Anybody remember from the US Under 31? What's it called? It's called R squared. Or sometimes it's recorded R square. Okay? R square is actually closely related to the coefficient of correlation. Okay? So the value of R squared is a number between 0 and 1. Okay? And what I'm going to write next actually is very generic, okay? Very generic interpretation of R squared. But every time when we evaluate the model, we basically have to provide problem-specific interpretation. You will see in a minute what I mean. So here is generic interpretation. Applies to all cases. Okay? So R squared is percentage of variability in target variable, let's call it y, which is explained by and attributed to variability in predictor variable x. Variability in predictor variable x. Okay? So this is generic interpretation, again, for all cases, for all problems, regardless of what it is. Okay? R squared tells you what percentage of changes in your target variable y is explained by the changes in your predictor variable x. Question, you guys. Do I want my R squared to be high or low? Low? I want it high, right? I want high percent of changes in target to be explained by my changes in the predictor, right? Essentially what it says basically is your Y, changes in Y are related to changes in X, right? So if my X truly has an effect on Y, my mileage has truly effect on the price, then changes in mileage will explain more and more percentage of changes in the price, right? The higher the better. The absolute best it can be is 1.0. That's ideal, right? So that happens only in one extreme case, when all of your points align nicely along the straight line. Okay? Your coefficient of correlation is perfect, +1 or -1. In this case, your R squared is going to be 1.0, ideal perfect model. Never happens in actuality. Okay? You will not find single case when you will have perfect R squared. But the closer to 1, the better. Okay? 0, on the other hand, is worse, right? The worst it can be. Okay? If your R squared is 0, that means that, yeah, you don't really have a model, okay? It's so crappy, it's unbelievable, okay? Do something else, try something different, okay? That's just not working out. Okay, so where do we find R squared? Well, let's go back to the output. Do you see closer to the bottom, there is a line that says multiple R squared equals 0.355 something, right? 3556. That is my R squared, okay? 0.355, okay? So how do I interpret R squared specific to this problem about car prices? Here's my interpretation. About 35.5% of changes, variability, changes, okay, in car prices are explained by and attributed to changes in car mileages, okay? So in other words, this one single variable, mileage, explains about 35.6% of all changes in terms of prices from car to car, okay? I take different cars, they all cost differently, okay? I'm going to ask myself, well, what causes the difference in the car prices? Well, about 35.5% of these differences, variability, is due to the fact that different cars have different mileages, okay? So that means that about 65 or so percent is not due to the price, right? Not due to the mileage, okay? So what's the reason for the other 65% of variability? Whole lot of things that were not part of this model, right? Such as number of accidents, right? As reported by Lemon Check Carfax, right? Is it manual or is it automatic car? Okay, color can make a difference, right? Does it have extra features, right? Such as built-in GPS, CD changer, sunroof, leather seats, anti-lock brake system, okay? Extra loud exhaust, I don't know, whatever, some cool rims, right? So all these other things, they explain, hopefully, the rest of the prices variability. And then, of course, when it comes to dealers, there is another factor, which is hard to quantify, which is called greed, right? So they will include some random amount in the price, knowing that you will negotiate and they will come down, make it appear that they give in, but not really, right? Because they still will be profitable after all that's said and done. Okay, anyhow, so my question is, okay, 35.5% R squared, right? Is that good or is it bad? How do I judge? Well, as much as I would like to have a yardstick, remember how we decided to discuss the strength of correlation. We said 2 points, 0.3 and 0.7. And by the way, they're not set in stone, right? I told you. You look at different textbook, you will see different things, 0.2 and 0.8, right? So just like this, 0.3 and 0.7, right? Well, no. In case of R squared, there is no such thing, okay? So the closer we are to 1, the better is the model. The further away we are from 1, the closer to 0, the worse the model. That's about it, okay? We can't say that if it's below 0.3, and it's a bad model with low accuracy. If it's between 0.3 and 0.7, then it's medium. accurate model, and if it's above 0.7, this is good. Yeah, generally speaking, you're probably right. But there are no such widely adopted cut-off points that separate good model from medium model from bad model. Okay, so just generally speaking, the higher R squared, the better off we are. Okay, and this is, by the way, by far one of the most important things. You ask any person who does data analytics professionally. That's the very first thing that I'll ask you. If you talk to a data analytics professional and tell them, hey, I built a model that allows me to predict sales based on population density, income, etc., etc., and the first thing that they'll ask you is what? What is your R squared? Because it tells them how good is your model. Okay, that's one of the most important things about the model that a lot of data professionals are looking for. Okay. Make sense? Are you with me? Yes? Okay, good. Now, things are not as black and white as I just told you. So essentially, I lied a little bit. Okay? Let me tell you a funny story. Okay? So today we're going to have a 12 minutes, right? Yeah, we have 12 minutes. Or maybe a little more. How about you stay late because you're passionate about data analytics? For a long time, in the world of statisticians, it was a belief, what I just described to you, okay? I don't need to see the model. I don't need to see anything about the model except tell me one number that about sums it up for me, okay? And in case of linear regression, that number was used to be believed R squared, okay? So statisticians, a lot of times, advocated, they still do, I guess, okay, that R squared will tell you pretty much everything and anything there is to know about the model, how well the model performs, okay? In 70s, I'm guessing, or 80s, I can't remember actually when it was, a British statistician with the last name Rsquared published a short paper, okay? And in this short paper, basically, he wanted to show that R squared and maybe a handful of other things is not enough to talk about a model, okay? Sometimes you have to take a look at the most important thing, a picture, okay? Believe it or not, just the magic of seeing the data set, the scatter plot, simple as that, okay? Visualizing what you're trying to model will tell you a whole lot about the model. Or what's this famous quote by Yogi Berra? You can tell a whole lot by just looking, right? You can tell a whole lot by just looking. And that's what Mr. Rsquared tried to emphasize. So let me show you amazing 4 examples, guys, okay? Let's see if we can go through them today. I'm not sure. All right. He published a paper with 4 data sets, really small data sets, okay? 4 of them. And that's why this data set is called Rsquared Quartet. In fact, it's so famous and popular that I believe it's built into R. So let's see. If you start typing Rsquared, yeah, you see that? We do have Rsquared built in. So go ahead and type Rsquared. I'm going to start a fresh script. You can do the same thing, okay? So go ahead and hit enter. And here is the data set. Whoa. Oh my god, hold on.